So people online, can you hear me and do you see the screen or do you see the slides?
Yes.
Okay, thanks very much for the confirmation. That's great. Yeah, as you remember, hopefully, yesterday we talked about, let's say, physics informed machine learning, the first part, and then I stopped just before deep operator neural networks. Well, I could now say on purpose. No, I was running out of time a little bit, and luckily Paris delved into that, let's say, perfectly. So I think we can mostly skip this. I haven't too many details on this. This was really just as an appetizer meant for what Paris would talk about. And so the main point, and I think he made it perfectly clear, is that before it was all function learning. Yeah, so from finite to finite dimensional input-output relations. Yeah, basically, I'm illustrating it here much simpler than what Paris had done. That, let's say, our network knows the function, hard-coded, and only accepts one input, namely at which point, that was the y in his case. Yeah, at which point do I want to, let's say, forward evaluate the pin? Yeah, whereas then in operator learning, we have this double mapping. Yeah, we want to be able to apply an operator to an incoming function and apply what comes out of this, which is a function. Yeah, operator applied to a function remains a function. Apply that to an input value. Yeah, so he had a slightly different notation. Yeah, so my operator, think of this as second derivative, for example, applied to a continuous function gives you, yeah, the second derivative of this. Should be a C2 function of the C2 function, and then you can apply this C2 or this twice differentiated function to an input, yeah, and get the output value of that. Yeah, and I try to do this with a, again, very simple case. And the way I try to illustrate it, that now the network does not have hard-coded the function. Yeah, think of the Poisson problem, the boundary conditions, the right-hand side. Yeah, but the function and these are then basis functions become inputs, say, inputs to the trunk and the other inputs to the branch network. Yeah, so that was a very brief summary. And again, you've seen this branch and trunk network that then gets kind of dot multiplied, yeah, basis times basis coefficients approach yesterday. Yeah, so I guess we can quickly skip over this. The only thing I want to kind of advertise already now, because that will be in the third part, we do exactly the same but differently in IGA nets. What is the same, what is different? So this idea of we have a basis in which we want the network to predict the coefficients, we stick to that. Only that we think, or well, that we do not learn the basis because we think in IGA we already have a good basis. Or well, maybe that sounds too provocative. We in IGA agree our basis is a B-spline or a NURBS or a THB or whatever. So kind of we agree a priori on the basis. So this flexibility of learning the optimal basis for this problem, we rule out from the beginning. Yeah, so therefore our, going back, our network that is producing the basis, so the branch network, we don't have it. Yeah, so in some sense it's a kind of in between a pin, but it's not learning just one problem instance. And it's also not a full deep O-net because we are not learning the basis. But stay tuned, we come to that. So I think, yeah, lessons learned from part one. We can skip over that because most of this was from yesterday. What I would like to do now is give you a brief introduction to geometric modeling with splines. So a couple of the topics have been covered by Stephanie in the very first lectures, Bézier, splines, etc. But I will put the emphasis a little bit different, yeah, especially here. So this is about how to make things fast. And in learning, yeah, while you have to train, it's all about speed, nothing else. And what I would like to do is kind of convince you that those of you who are familiar with FEM, who's familiar with FEM? Okay, or more or less all, that you actually have done lowest order IGA already. It's just a way of interpreting it differently. And let's start with exactly this. And now it's little bit an experiment because I try to draw there. Yeah, so let's look at the very simplest case, vanilla or textbook FEM, as you see it in a mathematics textbook. Yeah, so then it's always set. Let's assume we have an interval in 1D given. Yeah, we are creating a computational mesh. Okay, let's create the simplest how was it? This color. Yeah, let's create the simplest computational mesh. Yeah. Okay, then we define the basis functions. May I ask the people online, do you see what I draw?
Yes.
Yes. Yes.
Okay,
Yes.
good, good, super. Yeah, then basis functions. Okay, we are not doing anything fancy. We have the typical head functions. Yeah, so this one, that one, that one, and that one. Okay, these are our, let's say, basis function 1, basis function 2, basis function 3, basis function 4. Yeah, so in the slides that I will update, that you get, I will draw this much nicer than here, but here it's a little bit quick and dirty. Yeah, and then we use this basis to find our solution. Okay, let's do the same thing in 2D. I mean, it's obvious what we do. We can decide, yeah, we either take triangles, yeah, or a combination of triangles and quadrilaterals. Yeah, all is possible. And then this should be the mesh. And then on that, we define this basis function. Yeah, think of this as the standard head functions. For example, if we define the basis function for this point, it would be 1 here, and then goes down linearly to 0 over the support. Yeah, so I think this is an old head, literally and verbally, head function. Yeah, so, and then, yeah, mathematicians typically stop at the unit square. If we are really brave, we do a rectangle. Yeah, this is still not an engineering or industrial geometry, but what do we do then? Yeah, we also say, yeah, let's make just an approximation of this. Yeah, so maybe we need some more triangles here, yeah, because it's curved. And I guess you already get what I want. Yeah, so we would continue it like this. Where the problem is namely that, for example, here, we are missing something. Yeah, of course, we can make finer meshes, but conceptually, you can only approximate a circle with straight lines. You can never make it exact. So you can say, yeah, there are special elements, there are high order elements, all true. You can also say, I didn't dive into that. I just defined the basis on the nodes. Yeah, you can say there are Raviat-Thomas or Ranach-Haturek elements where they are somewhere not in the nodes or vertices, but somewhere else. All fine, but let's say, apart from these details, there are some conceptual problems that remain. And the one is, yeah, I'm again summarizing here the 3 steps. So mathematicians say the domain is given. How is the domain given? Yeah, so engineers, practitioners know as a CAD file or somehow, but it's not magically given. And then create a computational mesh. That is super easy to say. Very often that takes 2 months to get a mesh for a complete car body. Yeah, you get a mesh, but that's not analysis suitable. Yeah, not to speak of high quality. Yeah, so you can easily write that, but it takes very long. Yeah, basis functions also. What type of basis functions really on the nodes? Yeah, what properties should we have, and then find the solution? Yeah, we can ask, do we use Galerkin collocation, least squares collocation, all these things. And what I would like to do, yeah, so that could be a standard FEM lecture. What I would like to do is turn things upside down, so interpret FEM through the eyes of an IGA person. Yeah, because let's assume, and this is again 1D, that we are not starting from the geometry, create a mesh, and then define the basis functions, but we start from a basis on a reference mesh, not element, mesh. Yeah, so I have to, yeah, I make a reference mesh. I try to use the same colors somehow. Okay, with one. Yeah, let's make it simple. It's not an element, yeah, it's really a mesh consisting of two elements in this case. Then on that we define a basis. Okay, let's define this basis and this one. Then we define, and here you see this looks very much like the solution approximation that we had before. Yeah, we just defined a domain map. You could say it's a push forward. That should be blue through the control points. Okay, let me put X1 here. Ah, no, should be a different color. Then X2 here. X3 there. Well, technically it can be a curve in 3D, but I keep it very flat. Yeah, so it's just a linear stretching in some sense. Yeah, and through this basis, okay, I see the control point should have been in red. Yeah, through that, we have defined a push forward mapping. Yeah, so we get kind of the computational mesh, if you so want, but not kind of starting from the geometry, but starting from some reference thing. Yeah, let's give this the name reference domain, and then this the name physical domain, omega hat. Why am I putting this? So I haven't won anything. Yeah, the thing that I win is by specifying the reference mesh or the reference mesh and the basis, I have kind of defined what geometries I'm able to represent at all. Yeah, so I said I can move these points also in 3D, then it's a curve, but it's a curve consisting of straight lines. Why? Because the basis is linear. If I would give me here a quadratic basis, I could have quadratically curved, but still see zero connected curves in 3D. Yeah, and the same, I think in view of time, we will go over that. The same I can do in 2D. Yeah, so the point I want to make is this given magically a domain and we try to fill it from inside with elements is the textbook FEM version, but the IGA thing is more, we define kind of the playground or the toys that we have, the basis on the let's say the basis in the sandbox, and then we can move these toys from the sandbox into the real world, but only, let's say, in the way these toys operate. If they are linear, we can only represent with straight-sided lines. If they're quadratic, we can only represent up to quadratic domains. Yeah, and then, yeah, you can say these are basically the steps: basis on a reference mesh, forward mapping or domain mapping through the control points. We're finding the solution through the coefficients, and you see we are, yeah, silently we have unified the way we represent the mesh. Yeah, so X for me is always the mesh, yeah, and U is the solution. Yeah, we have unified the way we represent the mesh and the solution. Yeah, you can of course again pose the same question. Yeah, which basis with respect to which nodes, etc., etc. What is a good reference mesh? How to create it? Then, honestly saying, the problem of meshing now becomes the problem of how to place the control points. Yeah, questions there. And again, how do we find the solution? And the point that I want to make here, in some sense, we have cheated, or I have cheated, because I have made one difficult problem, turned it into another difficult problem, and sell it as the solution. Yeah, so the difficult problem in FEM is, or finite volumes as well, how do we create a computational mesh from a complex geometry? Yeah, that is the 2.5 months task for a car body. Now the problem is the same. How do we place the control points that, yeah, so the control points xi that kind of give us the mesh? Yeah, that's also maybe the people online who are not unmuted, unmute. Thanks. Yeah, so we have kind of given a new look to the same old problem, but we have now different ways, or maybe a different mathematical framework to solve this problem. Yeah, so this is more coming from the design optimization, because now we are kind of designing our mesh / our geometry from, yeah, the sandbox in which we have our predefined toys, the bases, and we are not coming from the geometry, which we then have to step by step discretize into a mesh. Okay, yeah, so I said this already, the push forward. As I will always talk about push forward, that means going from the reference domain, yeah, so our sandbox in which the basis and the reference mesh is defined, to, yeah, pushing this forward to the real world x, y, z, through setting the control points. Okay, and well, we can do that, and that's the point I want to make. FEM is a kind of, if you so want, lowest order IGA. Yeah, we can do this with the standard Lagrange finite elements, linear or bilinear, and so on. They have some very nice properties. They're interpolatory at the nodes. Yeah, so when you place a point somewhere, then the mesh really, yeah, has a mesh point there. Yeah. Yeah, the control points have a very local influence. Yeah, they exactly influence. If I modify this control point, it modifies this and this edge. Yeah, but again, a curved domain I can only approximate with a polygon, and the boundary is not smooth. Yeah, so if you're putting these two together, then between this and that one, if it's not a straight line, but if it is somehow, yeah, curved, there's a kink, a C0 step in your domain description. We can go to higher, let's say quadratic or biquadratic Lagrange finite elements. This property still holds. This is all nice and fine. We can approximate curved domains somehow by, yeah, piecewise quadratics, for example, or cubics, yeah, whatever you put here. Problem remains, these elements are still C0 coupled with the other. Yeah, so even if I have a, maybe I should draw here, if I have a nice element here, and then the next one like this. So this is all nice, but here I only have a C0 coupling. Yeah, so not so nice if you talk about fluid flow applications. So let's go towards IGA. Let's go towards splines. And I'm not sure if you have an idea where splines come from. So they have a very long tradition. So in, well, they were used in the shipbuilding industry for a long time, and then World War II, British aircraft used it to kind of sketch the wing shapes. Yeah, so what you had were wooden or plastic or some metal strips called the splines, and you held them in place by so-called ducks or docks or rats. I don't know who invented this. Anyway, yeah, some fixating points, and then due to the minimum strain energy principle, they bend it in a form, yeah, that had the minimum strain energy. Yeah, so it was the smoothest possible shape you could have, and this is what I already said. And I even found some pictures. This is from the, I think from the ship. Oh no, this is from the aircraft. Yeah, so these would be the ducks, I guess. And okay, no, I only have this picture. There are other pictures on Google if you look at them. And if you link this to what you saw in Stephanie's talk, what is the big difference between this spline and this mathematical spline that we or that Stephanie presented in the beginning? Exactly. Yeah. So here, to repeat it also for our online participants, the control points, yeah, so these ducks or rats operate as the control points. They are really on the surface or on the line of the spline, whereas, and that is what I wanted to draw on the next slide. So in what we consider a spline, we have control points. Okay, then we have which color is good? This one, kind of control polygon. But the actual spline, that's the one which I will draw in red now, it is interpolatory at the beginning and at the end, unless we do something against it. And then it, yeah, somehow is controlled, but does not go through the control points. Yeah, so this would be the spline. Whereas this would be the control polygon. And yeah, these are the control points. Okay, so a little 101. If you know all this, let me know, then we can fast forward. Who knows all this about splines? Okay, some, but not all. That's good. Yeah, so we start univariate, kind of 1D or one parameter. These are the first four B-splines, piecewise constant, looks very much like zeros order DG. Yeah, it's really, yeah, discontinuous here. Or finite volume. I mean, finite volume, zeros order DG can be seen as kind of similar. Then our well-known head functions, yeah, the piecewise linear ones, and from quadratic and cubic on, they behave differently. What is different? They are extending over, yeah, the quadratic extends over 1, 2, 3 elements. Yeah, so see this as an element, and they extend over 3. The cubic one extends over 4, and it continues like that. Yeah, means they have local support, but not as local as in higher order Lagrange FEM. Another thing different to Lagrange FEM, they are non-negative everywhere or over their support. Yeah, so second order or quadratic Lagrange goes through 0 and then in the negative part. Yeah, and they have something which you also don't find in higher order FEM. They have higher continuity. Yeah, so this one is once continuously differentiable everywhere here, and here it's just C0. This is twice this is C0, this here is C1, this here is C2. Yeah, it's always as many times continuously differentiable as this number -1. Yeah, so that already should give you some hint that such a thing I can prevent, yeah, that I can have a smoother, really not just C0, but C1, C2, whatever I pump in as a basis, continuity. Okay, now we come to how to construct it. It's basically very simple. We define a knot vector. A knot vector you can see as this. Yeah, so where do I put my points on which I build my functions in some sense? Yeah, it can be equidistant, it can be non-equidistant. Yeah, rule of thumb is, or a general rule is, the number of knots must be the number of basis functions you want to create plus the order or the degree. Yeah, 1, 2, 3. etc. plus 1. You can also have repeated knots. I come to that, but they must be non-decreasing. They don't have to be strictly increasing, but non-decreasing. Yeah, and then there is this recurrence formula from Cox de Boer, which basically says, well, if you have zeros order, yeah, then it's just 1 in the knot span where you want it and 0 everywhere else. Yeah, that is exactly this one. And then you are recursively building up higher order ones. Yeah, so the linear ones is a combination of the constant ones. The quadratic ones is a combination of the linear ones, which is a combination of the constant ones. Yeah, so you see this recursion very quickly gets larger. Yeah, and we need one small math trick, because it can be that we divide 0 by 0, and then we define this as 0 and not as not a number. In a couple of slides, I will tell you that Cox de Boer is nice for analysis, but not really practical in a computation, because all this involves ifs, and we never get 0 divided by 0. We get very small divided by very small. We have to, in some sense, if else that's all horrible, not performant, don't do it. But they have nice properties. They have the local support property. Over their entire support, they are positive or 0. They have local support property. This is the support. It goes from the knot where this basis function is associated with plus 2 d plus 1, the d plus 1's knot. Okay. No, that is not unlikely. It happens more often than you wish. The question was for the online participants, if I could say something about the situation when I divide by 0. If we look here, so this is a closed on the left, open on the right. So for example, a situation if these knots are repeated. I'm not excluding that knots are repeated. It could be that, for example, I have that the knot I plus 1 is repeated d times. That can happen. Not multiplication. Or not multiplicity. Then I have a 0 here. And if I evaluate it at exactly this knot, which is allowed, or same here, I can evaluate it at the left point, then I have really 0 by 0. And exactly. So basically, this formula is more theoretical and not, I wouldn't advise you to implement that one. Okay, but thanks for the question. So we see it has a local, less local than in FEM, but still local support. It's non-negative. It has this nice partition of unity property, what basically means at any point in your interval, you can evaluate the sum of all the basis functions and they sum to 1. A very nice property for the analysis, not so much for the geometric modeling. Okay, we come exactly to the point raised. Normally, we have a so-called open knot vector, which means the first d plus 1 knots are repeated and the last d plus 1 knots are repeated. Why? Because this makes sure that the knot is interpolatory at the two endpoints. So interpolatory means the control point lies exactly on the curve, which was the case in the let's say splines that we have in nature, but not in the mathematical splines. Therefore, we have to repeat this. And what we can do at the two endpoints, we can also do inside. So as I said, normally we have a d minus 1 continuity, third order C2 continuity. If we would repeat some of these internal knots, mi times, then we locally reduce the continuity to d minus m1. And technically, how many times can we repeat a knot? D times, well, technically we can even do it t plus 1, then it becomes dg. Yeah, then the two parts of this spline fall apart, then we have to do something. Yeah, but it's you can even create dg coupling with this. But yeah, practically I would say we go down to maximally d. That would allow us to have kinks. Okay, this is one of these examples. So you see here the knot vector. What do we have? We have quadratic ones. That means we have 7 basis functions. So we need 7 plus 2 plus 1. So 10 entries in the knot vector that we do have. It is open because at the beginning and at the end we are repeating 3 times. And in the middle we repeat it 1 time, and you see what it does. Yeah. So these quadratic basis functions are very nice and smooth, C1 smooth. Here at the third point, we reduce the C1 to a C0 continuity. Yeah, so that allows us to represent a kink. Okay, now we have splines, more precisely B-splines. They're called B-splines because they're a basis. So we can use this entire span, to span, as the name says, no, wrong. Good button. Yeah, to span our space. And apologize for this very overloaded notation. I try to put everything that kind of contributes to the space. I will later reduce the decoration of the S, but I wanted to be, formally correct. Yeah, the S, the space is defined by the knot span, is defined by the degree of the spline we want to create, and it is also defined by the space to which we map. Yeah, I said in the beginning, remember this example, I just take the control points as a line, and then I said, but I could also make it a curve. Yeah, so depending on which dimension of my control points I choose, there's this S, it becomes either a line or a curve in 2D or a curve in 3D or a curve in 20D if S is 20. Yeah, so, and I know I titled this geometric modeling, but technically you can model everything. If you have something that behaves univariately in a 20-dimensional space, univariately means along one parameter. Yeah, and it's a curve, in quotes, in a 20-dimensional space. Use splines and just put S to 20. Yeah. Okay, now we have the space. In the space, we pick the individual functions, by just kind of multiplying out the sum. Yeah, it's a dot product between all the coefficients and all the basis functions. And here I try to get rid of all this nasty decoration, just boldface C dot multiplied boldface B. Any questions so far? Okay, then one specific point. Yeah, so you might say, well, we have these control points. Yeah, so what can we do something more? Yeah, there are specific points. They are called the Greville abscissae, which is, well, you see a kind of average of a couple of consecutive knot vectors. And the amount of how many we average depends on the degree. Yeah, for linear ones, it would just be the one itself. For quadratic ones, psi I plus 1 and I plus 2. Yeah, we are averaging over 2 and so on and so forth. And they have a very special geometric interpretation because you call this the control polygon. Yeah, somewhere I drew it already without really telling you what it is. So what do I have here? I have here, again, the same knot vector as before. Yeah, so the one that is able to represent a C0 continuity in the third basis function, which is interpolatory at the beginning and at the end, quadratic. And let's assume this is my one-dimensional control point vector. Yeah, so it is, you have to read these values as the values in this axis. Yeah, it's at 0, at 2, at 1, at 1, at 3, at 1, at 2. That is just the height of these points. The question is, where on the x-axis, if you so want, do I draw the points? And you see they are not at 1, they are not at 2, they are somewhere in between. Yeah, they are exactly at this Greville abscissa. So what do we have? We have quadratic, so it's kind of an average over 3. Yeah? And if you combine the Greville abscissa, the x-axis here, and the height, so the C points as the height or as the y-axis, then you get this control polygon. And this is how you really model, geometrically model, yeah, if you would see this as a curve, with splines. Yeah, you are literally pulling these control points. And afterwards, I give you some interactive demo where I do exactly this, really pulling the control points. Okay, then there's something, and I just mentioned it and then forget it for all times, NURBS. I guess for engineers, NURBS are more exciting than for mathematicians because, yeah, what can NURBS do, what B-splines can't? NURBS can represent conic shapes. Yeah, a perfect circle, a B-spline cannot represent, a NURB can. And there is a nice mathematical interpretation of what NURBS do. NURBS are kind of a one-dimension higher B-spline. So let's assume here we have the origin. Yeah, this will be our NURBS. Yeah, so a perfect circle. If we go one dimension higher, and that is what we do by introducing this small omega, yeah, we just make it from kind of 2D to, yeah, so not x, y, but x, y, omega. And then you see these control points vary in x, y, but also in the height. Yeah, so the red one here would be the 3D B-spline representation of this curve. And if we are then freezing all these weights to 1, then we get a perfect circle. Yeah, and that is what are the NURBS. And that's the geometric interpretation of a NURB. The mathematical formula is just you have next to the B-splines, you have weights, and then you are averaging over the sum of all the B-splines with their weights. I think this formula Stephanie already presented, but yeah, I always like to visualize what these formulas try to do. Okay, for the moment, yeah, nice. With NURBS, we can do basically everything what we can do with B-splines and more, conic shapes. For the mathematician, this doesn't make too much difference because they have the similar properties. We can, yeah, continue with B-splines and keep in the back of our head that we could also do with NURBS. Okay, what else do we need? Well, I guess mesh refinement. I think yesterday or the day before, several times the question, did you do a mesh refinement or a mesh convergence study, was raised. So we have to be able to refine the mesh. And there are basically two. The one refine, let's say, in the resolution and refine in the approximation order. So my apologize. Here I go to P because in FEM, HP is typically the notation for mesh resolution and polynomial order. Yeah, we can do mesh refinement by something called knot insertion. I will tell that in some more detail. What it basically does is if you start here, it's always to read, we start here and go there. Yeah, if you start here with 3 control points, we are inserting, yeah, literally a knot. Yeah, so the 0.5 here is what we insert. We find new positions for the control points, and what you see, the shape doesn't change. Basically, it's shape preserving. We can start with something, or mathematically speaking, the spaces are nested. Yeah, if we start in this space, we can represent everything that lives in this space by a richer space. Yeah, and you see here, the 3 basis functions become 4. We can do something called order elevation, comparable to P refinement. The figures look quite similar. The difference is that we are not inserting a 0.5 in the middle, but we increase the polynomial order. So that means here we had D is 2. That means 3 repetitions of the 0. Now the D2 becomes a D3. That means we have 4 repetitions of the 0. Yeah, and yeah, you also see these basis functions become from quadratic, they become cubic. This would be, yeah, the illustration what happens with the curve. Yeah, so this is again not insertion. Yeah, so we have the old shape, and then we are representing it with more control points, but it is still exactly the same shape. Yeah, and with not with order elevation, yeah, the same. Take-home message, shape is preserved. And then there's something we do not have in FEM, so-called K-refinement, and that has to do with this order. Yeah, so in FEM, if I start with a C0, even if I increase the polynomial order, it remains C0 here. Yeah, with K-refinement, I can kind of do, yeah, not insertion and order elevation somehow. I'm not going more into detail at the same time. Yeah, so what I can do is I can kind of always, I can refine and stay at the maximum order that I can get at the P-1 order. That's a feature I can't do in FEM because, yeah, I can't control the C continuity. Yeah, and that gives you, but okay, that goes a little bit too far. That gives you very nice, yeah, convergence properties of IGA much better than in FEM. Okay, we now know everything, I would say, necessary for B-splines in 1D or univariate. If you want to go to 2D, and then technically 3D, 4D, and again 20D. Yeah, if you have some parametric property in 20D, you can just tensor product as many of them as you want. Yeah, and again a little bit overloaded, but I try to be lazy, so I don't want, these are the per dimension indices and degrees and not vectors, etc. And I try to put everything in these multi indices. Yeah, so it's not directly implementable, but yeah, this is a very compact way of writing it. And then my parametric domain is just this. Yeah, so see it as a hypercube from the leftmost to the rightmost knot in whatever dimension P we have. And the basis functions for, let's say, in 2D would look like this. And yeah, what you see here at the four corners, they are really interpolatory. That means they spike out to 1. And then somewhere here you see also some functions that are spiking out to 1. Yeah, that means that here and here and here, at least one or exactly one of the two components will have repeated knots, so that there are C0 there. Okay, we can define exactly in the same way the spline space. Now the only difference is that basically everything but the S is boldface, yeah, multi-D, if you want. And now get back to the domain mapping that I sold you as the other way of looking at FEM. Isn't this exactly what we are doing here? Yeah, we are defining a push forward from the parametric space to the real space by saying we fix the basis. Okay, we fix the basis here and there. We multiply it with some coefficients. Okay, here the coefficients were some coordinates in the XYZ space. Here they are the solution values, be it the density of a Navier-Stokes solver, be it, yeah, the velocity of the Navier-Stokes equations. Yeah, so basically this here, what we wanted to achieve, we can perfectly achieve with the spline space. Okay, and just give you some examples.
Excuse me.
Yes.
Just a small question to be sure. So the CIs, these are the control points, which are in fact
Yes.
the solution or the coefficients that will make up our solution finally, right?
Right. Yes.
Okay.
Thanks for the question. And they are the control points of the solution, but they are not the solution. So can you also see when I write something on the blackboard? Or camera is here, right? Here you could see me.
Yeah, almost.
Almost. I try to write as big as possible. Yeah, so in standard FEM, you have this property that, let's say I take the basis function I, if I evaluate it at the point, let's say I, it gives me a 1. What does that mean? Yeah, ui times bi at that point is ui. Yeah, so let's say the control points in Lagrange FEM are really the solution values at that position. Yeah, so you said I think at the beginning of your question, are the UIs the solution values and the control points? Let's say in Lagrange FEM, they are both. Here, they are only the control points. They are, unless you have interpolatory property locally. Yeah, so do you still see this? Yeah. It's like this control polygon. And this would be, you see this? Yeah.
Yes,
this would be the solution. So this would be a UI, whereas maybe the point here would be the solution value somewhere. Yeah, so simply said, the UI have no direct use. We cannot say, I take UI and then I know my solution value. No, I always have to evaluate this sum here, in the point xi where I want it to get my real solution value. Does it answer your question?
Yeah, thank you.
Okay, thanks for the question. Other questions? Okay, then some nice illustrations. So what this gray thing is, okay, first of all, this is a, what is it? The male rotor of some twin screw compressor. It has luckily 4 corners, yeah, the tips of the rotors. This is, let's say, the parametric domain, yeah, the square domain. And then by placing the control points, and again, the crosses here are not the control points. These are just, let's say, contour lines that tell you where, let's say, u and v are constants. Yeah, but placing the control points of this, the CIs or the XIs in a right way, we can represent such a geometry. Or here, yeah, a puzzle piece also has 4 corners in this case. Yeah, kind of what do? We take the control points here, pull them somewhere there. These have to be pushed inside, and then we get a parametric description of this puzzle piece. Question, this is, I think, which state is it? Indianapolis or no? Well, one of the US states. And I'm putting this because it has very accurate borders here, here, and there, and then a very fine, yeah, border there. What would your first association with that be? Is, let's say, such a tensor product parametrization the best choice possible? Or if you would just take this and create a standard finite element mesh, would you go with a, let's say, constant mesh size everywhere? Most probably not. Yeah, so we need something adaptive, and there is something adaptive called THB splines, truncated hierarchical B splines. I just touch it here just to show you it exists, and then yeah, show you some papers where you can find more references in this. What it basically does, it is refining locally where needed. Yeah, so you can guess this part here corresponds to that border. Yeah, this corner goes there. And then, yeah, here we need some more resolution. And in the upper right, it's all, yeah, very simple. And THBs are not, yes, sorry. Good question. Can we have holes? Yes and no. We can have holes by trimming. Trimming, I think in one of the talks, but I'm not sure. Trimming basically means you first do this and then artificially trim away the thing you don't want to have. But that requires a lot of hand work in your solver, because just because you don't see it doesn't mean the solver doesn't. You really have to trim it also in the solver away. Or what you can do, multi-patch. let's say if your domain is like this, and you have a hole. If you want to break this down into blocks that only have 4 corners, yeah, we can do it, for example, here. So 1, 1, 2, 3. Okay, no, we have to do it differently. This would work, right? 1, 2, 3, 4. And then same here. 1, 2, 3, 4, 1, 2, 3, 4, like this. Exactly. And therefore, we haven't, in IGA, people haven't solved all problems in the world. Yeah, it's just a new close to the same old, well, to an existing problem. Maybe the only thing that you could say is, here we are more looking at block, let's say macro elements, and not as at the real elements. But yeah, it would be bad if all problems would be solved, because then IGA could kind of close the book and start with scientific machine learning, for example. Any other questions?
I have a question, maybe more about the application. Can you introduce any tool, hopefully an open source tool, that can be used for like generating the mesh using the IGA?
You are exactly pinpointing the weaknesses. There is not really a, well, what you can do is use, I think it's called Cube or Cubic, a kind of a mesh generator. Cubic, right? Or Qubit. Well, a mesh generator that gives you a coarse or a macro mesh with quads or hexas, because technically what we need are only quads in 2D and hexas in 3D. What many different groups do, also what I do in my group, are really, let's say, application-specific meshing, or say blocking and then meshing techniques. Yeah. So for example, what we have done is you start with a point cloud, basically here. So this is just one example out of a larger thing. You start with the point cloud of the rotor. There's also some male rotor and female rotor, so kind of the negative of that, and some casing. You start with the point cloud, and from this point cloud, you're creating a parametric representation of your surface, which you are then mapping into the interior. Yeah, but that is really, let's say, ongoing research. It's not that there is one accepted open source package. So if you want, I don't see your name, but if you want, you can write me a mail. Everyone can write me a mail. I will answer that, of course. And then I can send you some papers on that.
Yeah, sure, I will. Thank you.
Yeah, you're welcome. Other questions? Yeah. It's also a big problem. And there's a conservation of, what is it, misery. It's a big problem. And also there, this is, let's say, this is one of the most standard ways of creating a parametrization. The technique that I just mentioned, what it is, we do harmonic mapping. What is harmonic mapping? Something like elliptic grid generation. Yeah, we kind of solve a nonlinear Poisson type problem just to get the mesh for solving the Navier-Stokes. But okay, if you want high resolution, you need to pay somewhere. And what we can do is, yeah, this color here, I didn't tell you, is kind of the determinant of the Jacobian, kind of the skewedness of an indicator of the skewedness of the parametrization. What we get, no, I don't have it here. In the break, I can find the slides and show afterwards. For really complex geometries, we get quite nice parametrizations, which are not that distorted. But yeah, the price is you solve a nonlinear problem just to get started with solving a problem. Other questions? If not, then let's go on. Yeah, and THBs are a little bit my favorite, but there are other techniques which are equally good. I just put, those that I know, and this is by no means complete. The most, let's say, prominent, most important ones. And again, let me remind you, if you click here, you go to the reference. Just to explain you how THB work graphically, because the formula way is a little bit more difficult. What you basically do is you take a regular refinement, a knot insertion technique, a regular refinement from one level to the next. Okay, then you decide here where this blue thing is, I need the finer basis. Yeah, and maybe that's the thing I should highlight. I'm not talking about I refine the mesh and then get new basis functions. I always think in terms of my spline space. Yeah, so I refine the basis. That's what I do. Yeah, because there are no mesh. There is no mesh. It's just basis functions. I decide in this region I need to find a basis. So in some sense, I keep those which I want. I kick out those which are completely inside. Okay, if I would now add them, you see this works, but it misses something. Well, it misses the partition of unity property. Yeah, if you would, let's say here, if we are adding up all the points along this line, they go to 1. If we do the same here, they go above 1. Yeah, and that is the trick. I'm going back and forth. Yeah, so the difference between HB, hierarchical B-splines, and truncated is, yeah, kind of those basis functions from the coarser spline space, that destroy the partition of unity are kind of adjusted. Formula-wise, it's a little bit more evolved, but that's basically what one does. Yeah, so a way to do local mesh or local basis refinement. Okay, so I think we found some answers to the two first questions. What type of basis? Yeah, I would say B-spline, THB. Where are they? They are not in the nodes, but yeah, in the Greville abscissa. Any special properties? Yeah, a couple of them, quite nice ones. What is our reference mesh? Mesh in quotes, yeah, the tensor product or the THB one. How to create it? Yeah, as a tensor product or as a THB one. Yeah, so now coming to the point, speed. This all looks nice, but Cox de Boer is not really super speedy, super efficient. I'm putting it up here, yeah, just to remind you of that. And I first thought to do a quiz, but seeing that we are lagging behind, maybe let's not take 15 minutes, but more minus. So just very briefly brainstorming. What type of function is this? Yeah, if I have a quadratic or a cubic one. Yeah, the function itself is not a cubic polynomial, but a piecewise cubic or piecewise quadratic polynomial. I thought to fill it out here, but I will fill it out in my room and then upload this for you. Yeah, so first answer is we have kind of piecewise quadratic or cubic or whatever once. If you sit down and calculate the function really based on the formula, it gets very large and very unhandy and practical. Not to speak of first derivatives, not to speak of second derivatives, etc. By the way, there is not even a closed form of higher than first derivatives. Well, you can write it down, but in no book I found it. It's really ugly. Yeah, and then, but that really takes a whole 50 minutes. Count how many operations do you have to do? Quite many. Yeah. And then the question, can we do better? Of course we can. Otherwise, this part of my talk wouldn't make any sense. So again, Cox de Boer. If we look at this F is, before I had, it is just all the coefficients multiplied by all the basis functions. But if we look which basis functions are 0, around some point. Yeah, so now this point where I want to evaluate it sits in this knot span between xi y and xi y plus 1. Yeah, many of them are 0, basically all that go to the right, and only the j's basis function and the d before are non-zero. Yeah, so I can kind of reduce this to this small inner product. Okay, for that I introduce yet another notation. Yeah, meaning around the point meaning starting from j minus 1, j minus d to j, I kind of filter out those, and all the others I neglect. Okay. Then, and I try to motivate what's coming on the next slides. Yeah, forget about the control points for the moment, just focus on this subset of basis functions. Okay, if we are in 1D is head function linear Lagrange. Yeah, I have two basis functions, namely the j's and the j minus 1. If I look at the recursion formula, yeah, it's just recursion formula. This one, it is either this term or that term. Yeah, because it's either this that is 0 and that is 1, or the other way around. Storage. Okay. Yeah, so I can write down this as a, what is it? It's a vector. For D is 2, quadratic. You can write down what it is. We need 3 basis functions which are active, which are non-zero. You can work it out, but you can also write it as the linear ones multiplied by a rectangular matrix. If you work this out, you see that's exactly what Cox de Boer would give you. Now, what is it for 3? First question. Exactly. And this other matrix has the same form. Yeah, so this is 3 by 2. It will be 4 by 3. Yeah, it's rectangular, it grows. And this is actually, there's only one school, the Nordic school, and in a very nice lecture notes from Tom Liesche, they dwell on this, that you can evaluate these B-splines as a chain of rectangular matrix multiplications. Yeah, and the matrices are given like this. Yeah, so he also proves it. I skip the proof. Yeah, we accept that it works. Okay. If we now look at the cost analysis, yeah, so what I try to do here is these are the matrices. They have always the form 1 times 2, then 2 times 3, up to d times d plus 1. Should be in brackets. Yeah, so d times d plus 1. Yeah, so if we store all the matrices in dense form, not optimal, but let's assume we do this, what's the cost of doing a matrix multiply? Well, it's the common, so 2 times the common dimension minus 1 for the multiplications and 1 lower addition per entry. And we have n times m entries, so that is the cost for a matrix multiplication. If we look from this from the left to the right, yeah, work this out. I worked it out here, calculated it, checked it with Maple. We get this expression. Yeah, what does it mean? We get a leading cubic term in the degree. We can also do it from right to left. Yeah, let's do it from right to left. Again, working it out, blah, blah, blah. We get a leading quartic term. So obviously doing it from the right to the left is more expensive than from the left to the right. Yeah, and yeah, it is really more expensive. This is now up to 7th or 8th order. If you need that in practice, I don't know, but already for, let's say, something that is practical, quartic, quintic, you see there is a big difference. Yeah, so we are here maybe at 200 or 300 versus something that is very small. Yeah, left to right stays small, right to left goes up. Okay. Derivatives. I told you if you just calculate the derivatives straightforwardly, so directly, it's very, very difficult. Or, well, very, very evolved. Again, based on this matrix representation, we just have a prefactor and then a couple of matrices in the original form and a couple of matrices which are differentiated with respect to this parameter. Yeah, so basically before there were a something minus xi and here was a xi minus something becomes a plus and minus 1. Okay, same question, or not same question. Yeah, let me skip over this. What they also show is, let me go to this. What they also show is that it doesn't matter where we put the derivatives, as long as we put r. Yeah, so if we want the rth derivative, we have to put r d's somewhere here. Can be from the first r's or the trading ones. Yeah, doesn't matter. We have to put r of these derivatives. Yeah, it's based on the two theorems or theorems I just skipped. Please just believe me that it's true. Otherwise, check this book, which is anyway a good source. Now, the question is, I'm looking at what does it cost to evaluate the r or its derivative? Well, there's a very small difference because we don't have to calculate this xi minus something. We just put it to 1. So that makes the difference between 4 and 6. Again, if we do all the math, if we put the d's in the first smaller r's to be d, we get something that is this, so quadratic. If we do it in the trading ones, we get something like this, which is also quadratic. So it seems like not too much. Yeah, so not really an order of magnitude that we win. But if we compare this, and you have to read it, yeah, so it should be actually a surface, but because it doesn't make sense to have a 4.5 derivative, it's just a discrete point cloud. Yeah, see it as there's a blue surface and a red one. And red is leading, and red is always a little bit higher than blue. Yeah, that is in the D direction. In the R direction, yeah, so this means here we have no derivative, here we have maximal derivatives. And obviously, if we have no derivatives, it doesn't matter where we put these non-existing derivatives. Yeah, so here on that border, red and blue are the same. And if we have maximal derivatives, so basically all r's are differentiated, it also doesn't matter because all r's are differentiated. Yeah, so see this as a kind of, there is a, maybe I should. So there is a blue line, and then there is a red line, yeah, which is always like a slightly elevated one. Yeah, and actually the biggest advantage of trailing versus leading, if we have, let's say, number of derivatives in the middle between the degree. Okay, so seems that the optimal evaluation strategy is from left to right evaluation plus trailing these. Yeah, that would be this cost surface or landscape. Question, can we do better? Of course, yeah, when asked such a thing, we could, yeah. Yes, that would be if we know we need function values and derivatives. So we could kind of tabulate the things that we already computed. Yeah, that would be one way. Or another way would be, I said, and I also remarked it's not optimal, that we store all matrices as dense matrices. And okay, for the low order matrices, there are hardly any zeros, but for the, for example, for this one, it's basically just 2 bands and the rest is 0. So we are calculating many more operations than really needed. So what we can do is yet another really great thing that is hardly used from this book. We did some modifications to that to make it, let's say, even more practical, what you basically do is you do the, so there's a for loop over the arm matrices, and then a for loop over the differentiated ones. So you see here, it is psi minus something, and here it is 1. So that is the differentiated psi. What we introduced are these masks. They formulated somehow differently. These masks are kind of a way to not check, do we divide 0 by 0? But if this is 0, then we divide mask by mask, which is 1, which is, no, we divide, what do we divide then? If this is 0 and this is 0, well, anyway, we divide something which reflects this 0 by 0 is 0 thing. And if we look at, and this here, the double dot and the dot multiply are element-wise operations. And if we now look how much this costs, that is the green one. So the purple one was the, is it the optimal thing? Now this is the green one. You see the green one is really much, much more efficient. So purple, green, or the same thing. Okay, this is maximal degree, maximal derivative. But here, if we have no derivatives, so basically meaning that, that this entire block is inactive, we just do this, it is still, this is somewhere around 200 ops, the green one, and this should be close to 400. So I think, unless someone finds an even more efficient one, for us, this is now the gold standard. Let's go over this. I come back to these slides. I just want to show you some performance numbers. We implemented this in Torch, in the C++ backend of Torch, because why am I so picky on the flop count? We have to differentiate all that for the training. So any flop I can save here, I save by a factor of whatever in the back differentiation. And what you see here, there are 3 colors on a quite decent AMD EPYC, on the ARM from Fujitsu, and on a not so modern graphics card anymore, but we also ran it on A40 cards. And what you see, let me just pick out one. Basically, if we just evaluate a single entry at a time, far too much overhead. But if we do, this would be 1 million. This would be, what is it? 100,000. We see it goes down drastically. At some point, the 2 CPUs kind of are saturated, but the GPUs, still go down. I think if memory wouldn't be a problem, and I mean, memory is at some point a problem with the back propagation thing, we really get down, from, what is it, 10 to the 6 or 10 to the 5, down to less than 10 to the 1, 5 orders of magnitude. Okay, let me go back here, because this was all nice and fine for univariate. You may ask, okay, how do I do it in 2D, 3D? Well, let me remind you of 2 basic properties of the Kronecker product. So that is how the Kronecker product of, product between 2 matrices is defined. It has a very nice property, the so-called mixed product property. So A cross B normally multiplied by C cross D is the same as the matrix products AC crossed with BC, if AC and BC exist. So if the dimensions are, let's say, compatible. And what that allows us to do is write, let's say, a cross product or Kronecker product between, let's say, the one univariate B-spline and the other, like this. So now some, what is it? I think the B and the C become identity matrices. Okay, now from here, I apply this step. I mean, I can write it like this. And I can do exactly the same with as many matrices as I want. I can basically say it is a matrix product of A1 crossed with a lot of identities, with a matrix product of I1, A2, a couple of identities, etc., etc. Okay. Now, let's assume we have pre-evaluated vectors B, yeah, univariate vectors B, and we want to compute the cross product. Yeah, this is now for 3D, and then dot it with F. One could say, okay, I have this. Why shouldn't I just, yeah, work out this cross product? Gives me, I mean, all these B's are just flat vectors. Cross product of flat vectors remains a flat vector. Yeah, it's just a very lengthy one. Why shouldn't I do that? And then that dot multiply with all the coefficients. I can do. Yeah, so here are some, yeah, what it would cost you or what it would require you to do. Yeah, and for example, if you're just varying, you keep the position in the first and in the second dimension and only vary the, let's call them UVWs or C3. Yeah, if I'm just varying the sampling point in the third direction, I would have to evaluate all this, even though it's not necessary. And a thing, and I think this is more severe, this F. I mean, what is F? F is a subset. Yeah, F is a subset of all the coefficients, and they are not contiguous in memory. Yeah, so example in 3D would be a tensor. If I start numbering along the X and then the Y and then the Z axis, yeah, and if I'm just picking out a small subset, yeah, the one in which so all the basis functions are non-zero at a particular point. If I flatten this, it looks like this. Yeah, so if I would say, give me the F, yeah, it means, okay, 8, 9, 10, 11 are contiguous, then it's a small jump. Okay, from the one tile to the next tile, it's a bigger jump. Yeah, so this, what I want to point out is this nice mathematical formula cannot compute it that simply. Yeah, so it means I always have to kind of first gather the right portions from my big memory vector and then do the multiply, the dot product. So what we found is a very nice algorithm in a paper from Fackler from 19. It's really called algorithm 993. Yeah, so it's a running gag. I always tell my students, please use algorithm 993, and they know what to do. But only my students, I guess. What this one does is it is kind of exploiting this property, yeah, and then it's starting here and peeling off one dimension at a time. Yeah, so in the beginning, we have to collect this F. Yeah, so the 8, 9, 10, jump, 14, 15, 16, 17, bigger jump, etc., etc. We, yeah, kind of have as many rows as the first dimension, and all the rest. And this is maybe you remember this from MATLAB. Yeah, so this is what we have as columns, and all the rest is consumed into rows. Yeah, reshape is nothing. No real copy, it's just a reinterpretation of data. Yeah, so we reshape F, take the first, in this case, the first univariate basis, dot multiply it. This gives us a vector. And then I have to reshape it again, but reshaping is just interpreting the numbers which are contiguous in memory in a different way with the second one, etc., etc. Yeah, so this is, as I would say, one of the most efficient ways to evaluate such products between, let's say, Kronecker product matrices, if one side is a Kronecker product, yeah, without really working out the Kronecker product. And yeah, now coming to this, you have seen this was for univariate, there we didn't need algorithm 993. This is now for quadratic, yeah, bivariate, so 2 dimensions. That means 993 has one loop, iterates 2 times, and you still see the same, yeah, significant gain if we evaluate many points at the same time. Same holds in 3D, and at some point here, I think here we really saturate the 32 gigabyte, but now we have some A100 with 80 gigabytes, so we basically can go some orders of magnitude higher. Any questions so far? maybe last words on this. We implemented this in Torch, in the C++ version of Torch, made a Pi wrapper with PyBinder wrapper around it. The code, and that is the underlying, let's say, the backbone of IGA-NETs, will soon be open source. So at the moment I share it, let's say, with students and collaborators, but it will soon be an open source thing. And if you don't care about IGA-NETs, but just want a very fast, B-spline evaluator in Python or C++, also just to send me a mail or Google that code and you can use it. So as at the moment, it's not it's still private or not open source, but will be soon. Okay, and then not insertion. That was the one thing. Mesh refinement, if you so want. Just reminding you of this slide, which we have seen before. And that is also very, very easy with this matrix representation. So forget all this technical things and just focus here. Well, the technical things are needed because it's not if we have one not vector and the other is completely different, then it's not insertion, then it's kind of mapping from one into the other space. But if we have a not vector and a refined one, so this one is nested in the finer one, then something called the Oslo algorithm. Also, let's skip all the details. What it basically does is it is going through all the knots of the finer one. Let's go back. What do we have to do? Let's say we have this and we have to find the position of the control points relative to the new basis such that the shape doesn't change. Okay, and we can do that by finding, let's say, for each pi, so for each knot from the finer knot vector, the span in which it lies in the old one. And then we are computing the coefficients for that particular B-spline function like this. So either we just take the old coefficients, if it's piecewise constant, or otherwise, this looks very much like this chain of R matrices. It only differs in where we evaluate it. We kind of evaluate it in a specific point or in specific points which are relative to the knot for which you want to find the control point. So I fully understand you're not following the details at this moment, and it was far too quick. But the message I want to bring here is when you give up this Cox de Boer thing and all the textbook math, but focus on or accept that these matrices, this matrix representation is there and is helpful. You can do a lot of things which are otherwise quite tedious with this. And of course, we implemented not the matrix multiply, but this and this. So for me, the matrix multiply is just a visualization to say, well, it's always this algorithm that is running under the hood. Okay, that brings me to the end of part 3. So no worries. The other parts are shorter, so we are not running too short on time. I hope that gave you a little introduction to B-splines for those who haven't heard about B-splines at all. For those who knew B-splines, I hope that at least the efficient evaluation was some new thing. And if you have any questions, please let me know.
Package we were playing with on the first day from Stefani. Does it implement these improvements or not?
It was from the sorry, you're right. That was the peak was somewhere here, was from this the original implementation of the, how is it called? spline lib, spline pi, yeah. And then we discussed how they implemented, how this is implemented, and I think now they are. I'm still not sure if you parallelize. Yeah, say single point evaluation should be as fast, maybe even faster, because for a single one, I go through the entire PyTorch, or not Pi, Torch overhead, and you implement it, or Spline lib implements it natively in plain C++. Yeah.
Thank you. So you were saying that you are not implementing matrix multiplication because since they are sparse matrices, you can like the algorithm that you showed before implements only the needed multiplication of the whole matrix multiplication. Is that correct? Okay.
Thanks. Yeah, that's exactly. I mean, if you look what's happening, here you have the division, and here you have a division, and here you have a multiplication. It's basically we do the matrix multiplication for exactly those entries which are not zero. And well, what is this? We are at some point, if you have a rectangular matrix and if you do it from left to right, it has to grow. This is what we do here. We are padding it with a 0 from the right and from the left, and then go to the next loop. So that is how basically it's a smart way of implementing this two-band matrix multiplication.
Thank you. Another question on the same algorithm. The first, the block tool, let's say, if I understand correctly, it implements the multiplication of the first D minus R matrices. Okay, these are the same both for the derivative and for the function evaluation. Okay. Then the next block of the algorithm, it seems to me, is only implementing the derivative computation, but we need also to compute the functional evaluation, right?
No, so if you say I only want the function, yeah, then also here 0r would be small r would be 0. That means, yeah, this would go up to D. D is the end, so there would not be any differentiated R. Yeah, so it is, you are not saying I'm computing everything up to the rth derivative. You can implement it, but yeah, then it would be kind of reusing, as you suggested before, reusing those things which are the same. No, this is really, let's say I want the second derivative. I only get the second derivative of the B-spline functions.
So if I want function and derivative evaluation, I would run your algorithm twice. Okay, thanks.
Or you could do it, let's say, up to here, and then have let's say, technically a branch, or you are spawning a new thread. One thread is calculating the values, the other is calculating the first derivative, the next one is calculating the second derivative. Yeah, but we haven't done that yet. Thanks. Any other questions? Or online? So if not, I would suggest we, well, not just suggest, because we do have the break right now, don't we? Yeah, we do have the break right now. So let's have the break and then continue at 11 with the other parts.